Okay, so now that we've discussed the transmembrane domain of the cis-loop ligand-gated ion channels, what I now want to talk about is I want to complete my discussion of the structure of the cis-loop ligand-gated ion channels before we move on to how it actually opens. Now, we need to talk about the ligand binding domain because that's really important in actually gating the channel. So is this pore forming domain, but the final domain I want to talk about is the intracellular domain, which isn't really terribly important as far as gating the channel is concerned, but just for our discussion to be complete, I want to talk about the intracellular domain. So I'm now going to talk about the intracellular domain. I'm then going to go back to the ligand binding domain and will then have the full structure of this channel, and we'll then talk about how it opens. Okay, right, so the intracellular domain then. So let me get another piece of paper. Right then, the intracellular domain. The intracellular domain of the cis-loop ligand-gated ion channels is often abbreviated to the ICD for short. So this stands for intra, which is the I, cellular, which is the C, and then domain, which is the D. Right, so what is this then? Well, basically, we've now discussed the pore-forming unit of the, we've discussed the transmembrane region of the cis-loop ligand-gated ion channel. So let me draw another picture of the cis-loop ligand-gated ion channel, and let me draw the structure of a subunit out again, because basically, this intracellular domain is going to be formed by the intracellular loops of each of the subunits of the cis-loop ligand-gated ion channel. So here is our cis-loop ligand-gated ion channel with these 5 subunits making it up. Okay, and now if we take just one of these subunits out, then we know that the membrane-spanning topology of this structure is like so. You have the amino terminus here. You then have this cis-loop in the extracellular domain, and we'll talk about the extracellular domain later because that's what's going to form the ligand binding domain. Okay, you then have these 4 membrane-spanning alpha helices which make up the transmembrane region, which we've now discussed, and you then have this M3, M4 loop, which is also called the intracellular loop. And this is going to be important in the intracellular domain. So, we're now interested in this loop between the M3 and the M4 membrane-spanning alpha helix. So basically, each one of these subunits is going to have one of these M3, M4 loops hanging down from it effectively. So let me draw them here. So here's this one's M3, M4 loop. Here's this one's M3, M4 loop. And then the M3, M4 loop from this one. And you can see the way I'm drawing it, what happens is all these M3, M4 loops come together basically at the bottom. So let me highlight these in the same colour. So here's one M3, M4 loop, here's the next, and here's the final one. So effectively, what's happening is you're forming like a basket, and it's often compared to a hanging basket. So if I draw this structure as though we're looking now from the bottom, so let's look at this structure from the bottom, what you'll see is you'll see these 5 M3, M4 loops. So here's 1, here's 2, here's 3, here's 4, okay, and here's 5. And they are hanging down from the bottom of this cis-loop ligand-gated ion channel like this. So I'll draw the cis-loop ligand-gated ion channel just as this sphere here. Well, circle, sorry, not sphere. Okay, so these are the M3, M4 loops, or the intracellular loops. Okay, and you can see that they're all coming together and forming like a basket with these holes between the M3, M4 loops. Okay, so you have these gaps basically in this basket here. So you've got one gap here, you've got one gap here, one gap here, one gap here, and one gap here. And these holes are known as portals. Okay, and these portals are available for ions to move through. So ions can move through the portals, and then when they get into this cavity in here, they can then gain access to the bottom of the pore, the intracellular aspect of the pore. So basically, any ion wanting to come into the cell is going to have to come through the pore, and then it's going to go into this intracellular domain. And by the way, this entire structure here, this is the intracellular domain, this hanging basket structure. And basically, it's now going to have to leave through one of these 5 portals. Now, why is that helpful? Well, imagine if this intracellular domain was not here. What would happen? Well, basically, you'd open the channel, ions would come through, okay, and what would happen then? Their trajectory would be perpendicular to the cell membrane, okay, so they're moving like so, on that sort of a trajectory, which is at a right angle to the cell membrane. So they're going to come through and they're going to go cohering off into the cytoplasm. Now, is that what we want them to do? Well, let's have a little think about this. So let's use the example of the nicotinic acetylcholine receptor. So I'll draw a nice simple picture of the nicotinic acetylcholine receptor. I'll just draw it as 2 sort of sides. Okay, so let's say this is a nice simple picture of our open nicotinic acetylcholine receptor. Now, what do we want to do when we open the nicotinic acetylcholine receptor? Well, acetylcholine is supposed to excite the postsynaptic cell, so we want to depolarize the cell membrane. Now, how are we going to do that? Well, basically, we open this channel, and this channel is permeable to monovalent cations. So it's permeable to sodium ions and to potassium ions. Now, let's look at the concentrations of sodium and potassium on either side of this cell. So the concentration of sodium on the extracellular side is 145 millimolar or thereabouts, and the concentration of sodium intracellularly is 12 millimolar. The concentration of potassium extracellularly is around 4 millimolar, and the concentration of potassium intracellularly is 155 millimolar. So, basically, the concentration gradient of sodium is favoring the movement of sodium in, and the concentration gradient of potassium is favoring the movement of potassium out. But you have a far larger gradient to potassium than you do to sodium. This is around a 40-fold gradient. This is a 12-fold gradient. Okay, however, there's another thing that we need to factor into this picture, which is the usual electrical potential difference across this cell membrane. So, let me just make sure we're all on the same page as far as understanding what electrical potential difference across a membrane means. So, when people say the membrane potential or the membrane voltage or the electrical potential difference across the membrane, what they really mean is the electrical potential difference from extracellular to intracellular. But it's generally just implicitly assumed that everyone realizes that we are going from extracellular to intracellular. So exactly what does this mean? Well, basically, if you had a little man standing in the extracellular compartment, he could measure the electrical potential, which I'll denote as big E, of the extracellular compartment, which I'll denote by subscript E. Okay, right. So he can measure electrical potential in the extracellular compartment. He can then move into the intracellular compartment and measure electrical potential, big E, in the intracellular compartment. So he can measure these 2 real numbers, okay? What he can then do is he can say, if I move from extracellular to intracellular, how much does the answer on my machine change? I.e., how much does my electrical potential change? So, what will this answer be? This is what's meant, by the way, by the electrical potential difference from extracellular to intracellular. It means if you move from extracellular to intracellular, how much will the electrical potential you're exposed to change? Okay, so this is just going to be the new electrical potential minus the old electrical potential. Okay, so this is what is meant by the electrical potential difference across the cell membrane. Now, it's usually around negative 65 millivolts. okay, which means that the electrical potential of the intracellular compartment is lower than the electrical potential of the extracellular compartment by 65 millivolts. Okay, now, both sodium and potassium are positively charged ions. They want to be where the electrical potential is lower, which in this case is in the intracellular compartment. So both of them want to be in the intracellular compartment. So the electrical gradient is going to help. It's going to work in the favor of this movement of sodium in. It's going to help the movement of sodium in because the sodium ions want to be in the intracellular compartment, whereas it's going to oppose the movement of potassium out because the potassium wants to stay in the intracellular compartment. So this one is going to get smaller and this one's going to get bigger, basically. Now, this electrical potential difference is not quite big enough to completely stop the movement of potassium out. In order to do that, you'd have to take the electrical potential difference to something like negative 85 millivolts. So this isn't strong enough, basically, to completely oppose the concentration gradient of potassium. However, it does significantly reduce it. So the result of this overall is that when you open the nicotinic acetylcholine receptor, you're going to bring a net movement of sodium in. We were always going to have a net movement of sodium in, but the important thing is that you're going to get a net movement of positive charge in, because the amount of sodium that will move in is going to be greater than the amount of potassium that will move out. And I should have said at the start, actually, that the nicotinic acetylcholine receptor, when it's open, is roughly equally permeable to sodium and potassium. Okay, so when the nicotinic acetylcholine receptor opens, it's going to get a net movement of positive charge into the cell through the movement of sodium ions in. What's this going to do? Well, basically, sodium ions have a positive charge. So when you move them inside of the cell, you're going to raise the electrical potential intracellularly. In addition, you're going to be moving them out of the extracellular compartment. So you're moving positive charge out of the extracellular compartment. So the electrical potential of the extracellular compartment is going to go down, whilst the electrical potential of the intracellular compartment goes up. Okay, so effectively this number here is going to go up, this number is going to go down. The overall electrical potential difference from extracellular to intracellular is going to become less negative. Intuitively, it's because originally this intracellular electrical potential was 65 millivolts lower than the extracellular electrical potential. But now if we raise this up and reduce this one down, they're going to become closer together. So the amount by which this one is lower is going to get less, i.e. this number is going to become less negative. So maybe it'll go up to something, I don't know, like negative 50 millivolts. The point is, this is known as depolarization of the electrical potential difference across the membrane. And what it's going to do is it's going to potentially excite other voltage-gated ion channels on the cell membrane and potentially cause an action potential. Right, so why does this matter? Why does the intracellular domain matter so much? Well, basically, when these sodium ions come in, we don't want them to clear off into the cell membrane. We want them to stay at the cell membrane. Because remember, what are they trying to do? They are trying to alter the electrical potential difference across the membrane that other proteins in the membrane are going to feel. Now, if they go cohering off into the cytoplasm, are they going to have that much effect on the electrical potential difference that this protein over here in the cell membrane is going to feel? No. Whereas if they stay by the membrane, they're going to affect the electrical potential that these proteins in the cell membrane feel more, basically. So we want them to stay at the membrane. So that's the purpose of this intracellular domain. It's to deflect the sodium ions or other ions that are coming into the cell. The sodium ions is in the case of the nicotinic acetylcholine receptor and also the 5-HT3 receptors. But the GABA and glycine receptors, those allow chloride anions into the cell. But the principle is the same, that you want the ions to come in and then basically be projected off onto underneath the cell membrane. So you need their trajectories to be parallel to the cell membrane. Okay, right. So that's the function of this intracellular domain of the cis-loop ligand-gated ion channels. Okay, in the next video what we'll go on to is the ligand binding domain.